The Gideon Lincecum chapter of the Texas Master Naturalists invites you to join Dr. Cheryl Metz, Professor of Geology at Blinn College's Brazos campus, and GLC members for A River Runs Through It, Geology of the Coastal Prairie, revealed by El Rio de los Brazos de Dios, the River of the Arms of God. We will start our virtual field session with an introduction to river processes. From there, we will travel upriver and backward in time, beginning at Stephen F. Austin State Park, continuing to Hidalgo Falls near Navasota, the site of early efforts to tame the Brazos River, detouring to Lake Somerville on Yewa Creek, a tributary of the Brazos River, and ending our field session at Stone City near Bryan, Texas, described as the most fossiliferous site in Texas.
Our field trip today will take us 62 miles up the Brazos River from Stephen F. Austin State Park west of Houston, upriver to the Highway 21 bridge at the former site of Stone City. Along the way, we will be stopping and looking at modern river features as well as cultural and geologic sites. During our trip, we will also be moving back in time within the Cenozoic period, sometimes referred to as the time of mammals. Starting in the present and Ice Age deposits at Stephen F. Austin State Park, we will step back to the lower Miocene at Hidalgo Falls, then into the Eocene at Lake Somerville, and finally we will end our field trip at Stone City, where we have traveled back 42 million years. If we continued upriver to the Route 413 bridge east of Rosebud, we would have traveled through all of the Cenozoic to reach the day where the dinosaurs went extinct. Our timescale chart for the Cenozoic also shows us changes in the shoreline as it moves seaward and then back in a land direction. Geologists refer to this shoreline migration as regression and transgression respectively. You can observe through the Cenozoic that these regressions and transgressions deposits form a stacked and shingled pattern across eastern Texas to reach their current position. The Brazos River, the longest river in Texas, is more than 600 miles long, starting in Stonewall County, Texas, and running down to the Gulf of Mexico. It travels through 70 counties, draining 42,000 square miles within Texas. The legend or explanation for a geologic map is given as a stratigraphic column, arranged such that the most recent stratum is at the top of the column and the older are below in order of their occurrence, taking from the idea that sedimentary strata are laid down one layer upon another. All the units shown in this stratigraphic column are found in our field trip area. The locations we will be visiting are indicated with their names.
We can use the stratigraphic column to identify the formation at each location we will be visiting by looking at the color and abbreviations shown on the stratigraphic column. For example, Hidalgo Falls is in the dark purple area labeled MO, which stands for Oakville Sandstone. Lower on the column, meaning farther back in time, is the olive area labeled EM for the Manning Formation found at Lake Somerville.
Here is the same field trip location shown on the Google Earth satellite map. Notice that on the image, the Brazos River Valley is much easier to identify north of Hidalgo Falls.
Before we head off to our first field session site, we have one more topic to discuss. How do rivers behave, and what makes them such good places to learn about geology?
So here I've drawn sort of a little cartoon of the Brazos River. Brazos is a meandering river, meaning it's making these loops. They're called meander loops. This would be a meander bend. The river flows in this direction. Now, one of the things that meandering rivers do, since they're flowing across a low gradient area, is over time they're going to migrate from one side of the valley, pretend like this is the valley wall, to the other side of the valley, which is out of the cartoon here. As they're flowing and they're moving side to side over time, they're also cutting down. But because we are so close to sea level, even though we're 80, 90 miles in, looking at elevation, there's, we're not that far above sea level. So they can't do much what we call down cutting. We can see the down cutting behind us there in the Stone City Bluff and some other places across the river here at the cut bank. So what makes these features, the point bar we're standing on, the cut bank that's on the opposite side of the river, is the velocity of the water as it's flowing. So here we have this bend. The water as it comes, here's our meander bend. As the water comes around the corner here, it slows down on the inside and it deposits gravel, sand, whatever. This is our point bar, okay? As the river water is going around the curve here, it is speeding up on the outside and it's eroding the outside of the meander bend, and we get that what we call a cut bank. So here I have my point bar with deposition taking place. On this side, this is my cut bank. Here. Okay, and we have erosion taking place over here. So we have erosion here. I'm just going to put an E. And we have deposition. I'm going to put a D for that. Okay, and that's what, this is what we're seeing behind us. So as we look up here, we have the cut bank on the outside of the meander. That's forming that cliff. And we are standing on the point bar. So as the river has flowed across this area, the water velocity slows down. Anytime water slows down, we get deposition. Anytime water speeds up, we get erosion. So here we can see sand and little bits of gravel and such. Depending on the velocity of the flood, the height of the water, what it was carrying, we might find different materials on the point bar. We can see some trees over here that were washed in and buried. It could be other things.
Is there like a timeline for it, or is every river different, like how often they swap sides?
It depends on the river. Yeah, and it may be very gradual. In some floods, they have what they call a avulsion, and it just will literally switch to the other side of the valley. Okay.
So material that erodes from the cut bank,
it's going to move. It's going to move its way downstream,
and so find itself on some point bar.
Yeah. Well, so there would be another point bar here. There's the inside of a meander. This little meander. There might be some here. Erosion here on the outside, and then deposition here. So these areas are all our point bars. Okay, so the river, this material gets eroded and it's moving downstream, okay, over time. The meander itself is moving downstream very gradually. Okay, so these aren't static features. So sometimes what happens is that, I didn't quite draw it curvy enough, as two meander bends get close together, they may actually erode through and join. And what you would see out here, let me tilt this, you might see what we call oxbow legs. And this here, so here's an oxbow lake, will give you a shot of an aerial photograph with these. And what an oxbow lake is, it's a meander that has, as this has eroded and this has eroded, it's come together in it. They've cut off the meander loop here, and we form this oxbow lake. Okay. Over time, with each flood, this will gradually fill in, and it will just be a low depression called a meander scar.
Having learned about how rivers change over time, we are ready for our first stop at Stephen F. Austin State Park, shown on the map with a red dot. The land that forms the park was deeded to the state of Texas by the San Felipe de Austin Corporation in 1940 and opened as a state park the same year. The park contains a mix of upland and river bottom ecosystems that are heavily influenced by the Brazos River. The Gideon Lincecum chapter maintains a native plant demonstration garden at the entrance to the park and participates in a number of other projects at the park. Before we hit the trails, we need to learn about the geology of the area.
Stephen F. Austin State Park is located on the Brazos River west of the Houston metropolitan area, seen to the east. It is the southernmost of our field trip locations. The geologic map for the area shows the Brazos River Valley sediment in bright yellow. Notice how the Brazos River itself occupies only a very narrow part of the valley. Adjacent to the river to the west are older quaternary strata that the Brazos River has cut down through. Often ice age fossils such as teeth and bone can be collected off the gravel bars downstream from here. Looking at the topographic map for the area, you can see the older quaternary deposits at higher elevations to the west. Another feature of note is that the 1960 base map and this 1980 revision shows that the river channel has migrated.
The course of the old meander loop, just above the current meander loop that has now migrated downstream, can be seen also in the Google Earth image. And now, it's time for us to join members of the Gideon Lincecum chapter out on the Barred Owl Trail at Stephen F. Austin State Park.
As we make our way down the Barred Owl Trail at Stephen F. Austin State Park, we'll take notice now we're in what's considered the upper hardwood forest of the state park, and later on we'll get down to the bottomlands closer to the river. The Barred Owl Trail is recommended many times to visitors because it gives folks a pretty good up-close look at the Brazos River. Take a look at these grasses here. Take a look at the hardwoods, the elms primarily, a lot of oak trees, Bermuda grasses that grow up here on the upper part of the trail. So as we approach the cut bank here on the Barred Owl Trail, we'll see that we're still on the upper part of the park system relative to the riverbanks. The Brazos River gets its name from the Spanish word Rio de los Brazos de Dios, the arms of God. Where we're standing now, this cedar rail fence has been moved back 3 times since in the 10 years or so that I've been coming to this location. The water's risen right up here where we're standing each of those times. Major flood events go back many, many years, but most recently we have the Tax Day flood in 2014, 11 months later the Memorial Day flood in 2015, and then of course Hurricane Harvey, August of 2017. As a result of these floods, we've had accelerating changes in the erosion of this location. Many of the changes take place upstream, many downstream, and of course across the river too, as you can see here. I've been told that through those years, the Stephen F. Austin State Park has gained over 75 acres and gained and lost over 75 acres since 1945, when the park was purchased from the City of San Felipe Corporation. Where we're standing right now, upstream as the egret or the crow flies is about 75 miles to Hidalgo Falls in a straight line. Downstream in a straight line to the Gulf of Mexico is about 100 miles. If you take into consideration the winding and turning and north and south movements of the river itself, we could probably double those numbers to get river miles. Okay, now we're going to move from the scenic overlook portion of the Barred Owl Trail kind of upriver, and then a drastic downward trail towards the bottom of the actual riverbank. If you'll notice, right now we're seeing a big transition in our ecosystem from an upland forest type ecosystem to more of a riparian system. There's a huge difference in the tree species, more sycamores, willows, and a larger abundance of the inland sea oats and the other grasses you'll find in a bottomland riparian ecosystem. Here we are coming up closer to the river. This part of the trail actually is new. Where we're standing right now, down below us is where the trail used to be. We actually lost about 10 feet of riverbank in the event right here, and if y'all have an opportunity to visit, you can actually see the old fence line down there at the bottom. Here we go. I would consider that to be erosion. I promise you, next time the river comes up, this is going to fill up with water and probably get pushed out. Where we're standing right now, we were actually in the Harvey flood event and the other two. The water would have been over 30 feet above our head. So what was once a steep bank and somewhat of a scenic overlook is now one of the easiest access to the river for fishing within the state park.
There is no question that the processes of erosion are in evidence at Stephen F. Austin State Park. Here we are seeing from the riverside the overlook where we stood on the Bardow Trail and saw the erosion accelerated by recent flood events. If we look back in time at this same stretch of river, we can see the movement of the Brazos River within its valley. This historical photograph shows the Brazos River in 1930 with the 1995 boundaries of the park superimposed. We can see the 1930 river channel cutting through what is now the riparian bottomland portion of the park. And if we look at an aerial view of the park from 1995, the outlines of the former river channel can be plainly seen. We've enjoyed our exploration of Stephen F. Austin State Park. Being able to see the upland ecosystem in such close proximity to the riparian bottomland allowed us to see the contrasts and similarities in the trees and grasses growing in each ecosystem. Spending time on the bank of the river as the water flows past in an endless stream to the sea engenders both a sense of peace and a respect for its power. We must move upriver to our next stop at Hidalgo Falls. On the way, we will learn more about how the river changes and how we can read the story of those changes using maps and historical images.
Let's move upriver from Stephen F. Austin State Park to an area 3 miles northeast of where Highway 290 crosses the Brazos River. Here we can see changes in the river morphology over a period of time. Let's take a look at those. Here on the 1961 Daniels 7.5 minute topographic map, we can see many of the features that define a classic meandering stream such as the Brazos River. We have 7 prominent meander bends displayed. Each of these bends has an inside area called a point bar in which deposition is taking place as water slows down around the bend. On the outside of the bend, which is called the cut bank, we have erosion taking place. Some of these bends come very close together, forming a very narrow area called the neck. To the south here we have 2 oxbow lakes. One time these were part of the river channel, but they have been cut off and are now separate. Over time these will fill with sediment and become meander scars. The river is constantly changing, and if we go back in time we can see these changes. We can do this by looking at older topographic maps. In 1961 we have 2 oxbow lakes. If we go back to 1900 we have 1. You can see it here labeled Old River Bend, and that the river channel just to the south of it is our second oxbow lake. Again, we see this narrow area between meandering bends called the neck. It is at this point where the channels can cut through, forming a cutoff or a bypass. Let's return briefly to the 1961 topographic map and look at our river features again. Our main channel in blue, the position of our point bars, the cut bank on the outside of the meanders, and our two oxbow lakes. Now let's move forward to 1989. In 1989, the Daniels topographic map was revised. What's nice about this revision is that it kept the 1961 map as what we call a base map, and the newer features were superimposed up on top of the old. Here we can see the 1989 Brazos River channel in blue, cutting across the meanders of 1961. The area that was labeled neck in 1961 has now been cut through, forming a cutoff that bypassed the former meander bend. Meander bends themselves have migrated southward, as you can see by these arrows. Our two oxbow lakes are on their way to becoming meander scars. Rivers are constantly changing, and the Brazos is no exception to this. Its meanders have straightened, moved southward. Over time, the river may move to the other side of the valley, new meanders form, new oxbow lakes form, older ones filled in. One thing is constant, it's change along the river.
We have arrived at Hidalgo Falls, the second site in our field session. Hidalgo Falls is located west of Navasota, Texas. Approximately 5 miles south of the falls, the Navasota River joins with the Brazos River at Washington on the Brazos Historical Site. Hidalgo Falls is identified on the Google Earth map with the red dot.
Hidalgo Falls is located approximately 5 miles northwest of Washington on the Brazos State Park. Here the river cuts into Miocene age strata of the Oakville Formation, shown on the geologic map in purple. The topographic map for the area notes a series of rapids. These can be easily seen on the Google Earth satellite image. These rapids have formed within the river as it flows across an interval of very hard, well-cemented sandstone layers within the Oakville Formation.
Now that we've been introduced to the geology of Hidalgo Falls, it is time for us to venture down to the river to see this unique site for ourselves.
Well, we've moved from our previous stop upriver here to Hidalgo Falls. We're standing on the Oakville Formation, which forms the falls. If you look behind me, you can see that there's a series of small little rapids and falls that this water is coming over. The Oakville is a series of layers of clay and these hard sandstones. When the Brazos River encounters the harder units, it's harder for it to cut through. So what we get is rapids, falls. The water will become channelized as it tries to bypass the falls, and you can see this off over onto this side. And most of the times the rock unit here is exposed. As water levels come up during rain events and we get flooding, water's moving downstream, the water level in the river will gradually rise, and the rocks here will be covered. As water begins to move over the exposed outcrop here, it will pick up gravel, smaller rocks, maybe about this big, and as the current moves, it will start grinding what we call potholes. And if you look over here, we can see a few of these potholes. We'll look at some other ones later where they have much better definition. But here you can see this depression. Here's one. Here's one. And what happens as these little stones and such get into the pothole, the water current will make them go around, and essentially they become deeper and deeper and larger and larger. And they may actually merge, as we are starting to see here. And they're wearing away the Oakville sandstones. We're going to take a little closer look at some of these potholes here that we have at Hidalgo Falls. And you can see that there's very large ones, some of them still filled with water. There's small ones. But I want to talk about a little more about pothole formation. So as the water level goes up, water begins to flow across here. What happens is the larger, what we call the bed load of the river, that material that's traveling along the bottom of the river bed, it's being transported. As the flood increases, the velocity increases, larger material can be moved downstream. Here what we're having is that because of this uneven nature, these particles will get caught and they'll get into a depression, and then they'll start circulating around, and the pothole will be getting deeper and deeper and larger and larger. And in one here and here, we can see some of these cobbles to larger gravel-sized particles that are forming the pothole. The really nice, well-rounded one, and there's one in this one. Let me grab it for you here. Sometimes geologists like to call these grinders because they're grinding the pothole as the water is moving across it. The pothole gets deep enough, these larger particles get essentially trapped within here. They can't get out. All they can do is swirl around and make the pothole deeper and deeper and bigger and wider. And you can see some grinders here. You can see a couple in here. Now, the type of material you see in there, if you had something like I just picked up, which was a harder rock that was quartz rich, it's not going to, other than it got rounder as it's moving around, it's going to be there a long time. If you have a piece of limestone that gets in here and becomes a grinder, not only is it increasing the pothole, but it itself is also getting smaller and smaller and will eventually disappear. So the type of rock it is and its hardness is important on how long it's going to last within the pothole. So most of the things you see here, even in this gravel-sized material, it's little pieces of quartz or chert, which is a different type of quartz.
While we were visiting Hidalgo Falls, Patty Carruthers, the on-site manager, shared with us the local legend that some of the potholes become so large and interconnected that a person can be pulled down into one pothole and come up in another downriver. Approximately 1.5 miles by river downstream from Hidalgo Falls are the remains of a lock and dam built in an early effort to tame the Brazos River. The site is accessible only by water. It is easily located on both the topographic and the Google Earth maps of the area. From the Galveston Daily News in 1910, in the improvement of the Brazos River and making it navigable from its mouth to Waco, the government has undertaken a work which is destined to be of far-reaching influence on the inland commerce of Texas. Projects to tame the Brazos River, whether for flood control, irrigation, or commerce, were the subject of much public interest from the 1890s through the end of the Progressive Era. Following a monumental flood in 1913, reported to be so extensive that the Brazos and Colorado rivers merged, creating a sheet of water 40 miles wide, community and government leaders joined forces to pursue improvement projects with the dual goals of flood control and improved navigation. Of these, one of the most ambitious was a series of 8 locks and dams proposed between Navasota and Waco, Texas, thus extending the navigable portion of the river above the historical limit at Washington, Texas. Congress improved funding for 4 locks and dams, including Lock and Dam Number 1 near Navasota, which was completed in 1915. The lock and dam suffered a structural failure shortly after it was completed. By 1919, the project was declared a failure. These ruins are all that remains of the dream to extend navigation northward up the Brazos River. We have had a really fabulous time here at Hidalgo Falls. We were able to explore this unique environment and learn all about potholes and grinders. Who knew that there were rapids on the Brazos River so near to Houston? And the ruins of the dam and locks were so interesting. I wish we had more time to explore, but we have a lot more to see today, and we have to move on to our next stop. We want to thank the Texas Rivers Protection Association, which owns land adjacent to the falls, and their on-site manager, Patty Carruthers, for giving us the opportunity to visit today. As we continue upriver, we are going to take a detour over to Lake Somerville on Yewa Creek, a tributary of the Brazos River. But before we do, we need to learn more about point bars and what can be found there.
Point bars are a good place to look for fossils because since the river is going slower at the point bar and more faster on the outside of the meander, things get deposited on the point bar. Anytime water speeds up, you get erosion. Anytime water slows down, you get deposition.
And if the water level is going down rather than up, then they'll lie on the surface.
Yes, because the velocity of the river is dropping as it's going down. So in flooding, those large boulders we see here, they may be a piece of sediment being transported downstream. Whereas during normal times, where the water velocity is slower, it may only be able to move grains of sand.
It is not uncommon to find petrified wood in the gravels of the Brazos River. In places, large petrified logs have been eroded from Eocene age strata and deposited upon the point bars or as medial bars in the middle of the river. The process by which wood becomes petrified is called permineralization. This occurs as minerals such as calcite or silica fills in the cells or pores within wood or bone. The original cell structure of the wood is often preserved to a point where the genus of the tree can be identified. In the case of these logs, the silica comes from volcanic ash deposits within the Eocene strata.
Lake Somerville was created in 1967 when Yewa Creek was impounded to form a reservoir to provide flood control, water for irrigation, and a site for recreational activities. The location of the outcrop that is our destination is shown at the east end of the lake, designated with the red dot.
Upstream from Hidalgo Falls, where Yewa Creek joins the Brazos, the river moves on to older Eocene age strata. Just west of this juncture at Lake Somerville Spillway is a good place to observe the changes in the Eocene shoreline as it moves back and forth across the area, leaving behind both terrestrial and marine deposits. The Lake Somerville Spillway is located at the east end of the lake where it empties into Yewa Creek. Excavation for the spillway exposed 30 meters, 100 feet, of late Eocene Manning Formation along its southern side. The Manning Formation can be seen on the Geology map as the olive-colored unit labeled EM bordering the lake shore. To reach the outcrop, you park at the overlook shown on the topographic map, located on the southeastern side of what is an emergency spillway during times of high water levels in the lake. The outcrop is a steep slope running in a southwest to northeast direction. Here on the Google Earth satellite image, you can see the Yewa Creek outlet in the northwest corner, The emergency spillway is the concrete and water-filled rectangle in the center, with the overlook parking area to the southeast. Our outcrop can be seen emerging from the clump of trees and trending off in a northeast direction. The easiest way down to the base of the outcrop is to follow the service road from the overlook parking area down to the spillway floor and walk back to the outcrop. As the spillway outcrop comes into view, you can see looking up from the spillway floor many different layers forming a series of slopes and benches. From the base to the top, we will examine the outcrop's major units as they record the change from terrestrial environments at the base, then into marine, and then back into terrestrial as the Eocene shoreline migrated first landward across the spot and then seaward again. Here is the stratigraphic column or measured section that was made for this outcrop. It depicts graphically the data and measurements made on the different layers of rock, their thickness, the lithology, the type of rock, the hardness, does it form a slope or a ledge, observations on various layers such as what fossils they contain, or sedimentary structures such as ripple marks or horizontal bedding can also be included. The total thickness of the outcrop is 30 meters, about 100 feet. Common lithologies are sandstones, mudstones, lignite, a type of coal, and tuff, an altered volcanic ash. On the right is shown which layers are included in the major environmental intervals based on the interpretation of the data collected. Note that the types of lithology which predominates any interval is variable from one to the other. Only about a meter or so of the basal terrestrial interval is exposed at the base of the outcrop. Here a mudstone can be seen overlain by a half a meter of lignite, which is in places underlain by a white ash deposit. The white ash can be seen in contrast to the overlying lignite. This lignite is interpreted to be of freshwater origin and the underlying mudstone floodplain deposits. Of note is ash layers and other sediment of reworked volcanic material are common in the Manning Formation and can be seen here at the spillway outcrop. The ash was deposited as airfall ash that drifted in from huge eruptions from volcanic centers in western Mexico and the western U.S., including West Texas. The middle marine interval is approximately 15 meters thick. It is made up of several smaller packages of interbedded sandstones, mudstones that contain lignite horizons, tuffs, and ash layers in the lower half of the interval. This interval is interpreted to have deposited in association with a deltaic center that switched back and forth across the area at various times. Deltaic sandstone units stand out in relief because of the high silica content from reworked ash that makes them more resistant to weathering and erosion. The mudstones contain reworked sponge spicules, marine microfossils and trace fossils, as well as macerated plant material. Pollen studies identify the lignite as brackish water in origin. Reworked burrowed discontinuous ash deposits can be seen associated with several of the lignites. Capping the whole interval is a very hard, fine-grained sandstone with quartz cement called a quartzite. The sandstone represents a shoreline sand deposit exhibiting crossfitting, burrowing, and root traces in its upper surface. Of note, this quartzite is reported to have slowed down the construction of the spillway because it was not initially recognized. The upper interval at the spillway outcrop is terrestrial in origin, laid down as the shoreline moved back over the area in a seaward direction. Overall, this interval is 9 meters thick. To examine it requires a little bushwhacking into the tree line at the west end of the outcrop below the parking area. Here, a thick freshwater lignite sits directly on top of the marine quartzite. Above the basal lignite are mudstones representing floodplain deposits that contain a thinner lignite seam of less than 1 meter. The mudstone can be split along bedding layers to reveal bits and pieces of carbonized wood and leaf fragments. Capping the interval and incised into the underlying deposits is a well-sorted, fine to medium-grained fluvial sandstone containing trough and inclined cross-bitting. The upper surface of this fluvial sandstone is at the level of the parking lot. Before we leave and head upriver again, let's take in a view of Lake Somerville.
We have arrived at the last site in our field session, Stone City, located where Highway 21 crosses the Brazos River west of Bryan, Texas. The highway bridge at this location was known to generations of Texas A&M students as the Whiskey Bridge. At the time, Brazos County, where Texas A&M is located, was a dry county. The bridge crosses the Brazos River into Burleson County, where whiskey was readily available. Stone City is denoted on the Google Earth image with a red dot.
The Stone City outcrop, sometimes known as the Whiskey Bridge outcrop, is our northernmost field trip location. The outcrop is on the southern bank of the Brazos River, just west of where Highway 21 bridge crosses the river. The strata of interest here is the Eocene in age Cook Mountain Formation, of which the Stone City is a member. The strata here is totally marine in origin, with a very diverse mollusk assemblage. It is not unusual to meet fossil collectors from across the state or even the world at this location. On the topographic map, you can see the outcrop locality is located along the cut bank of the river. In a southeast direction from the Highway 21 bridge, notice the Mulholland Slough, an oxbow lake between the Brazos and Farm Road 50. At this location is a Texas historical marker which documents the existence of an old levee system built in response to flooding, but in 1913 contributed to 180 deaths locally. This is the same flood that initially damaged the number 1 lock and dam south of Hidalgo Falls.
Both the Stone City outcrop and Mulholland Slough and Oxbow Lake can easily be seen on the Google Earth image. The fossil horizons in the Stone City outcrop are marked in red on the left-hand side of the column. These are the areas that we will be exploring today, focusing on the Moseley bed and the glauconite beds.
Here's our map. The Moseley is up there where this tree is sprouting out. So we can see some layers below it. This one is sort of very silty. That's a grain size smaller than sand. Usually it's barren of fossils. We're not going to pick up the fossils till we start getting to the glauconite. And there's several layers of glauconite. The big thick one we were collecting out of here, that's the main glauconite. We've got a sort of sandy, silty bit in between. We have another higher glauconite layer here. And then we have this silty unit. We have a little glauconite unit right under the Moseley there. Most people collect out of the main glauconite because it's just so well exposed. But here we can see this different layering quite easily. One of the things I've noticed here in this block of Moseley, if we look closely, we can see a lot of these sort of little rounded, what look like concretions. These are actually burrows, similar to what we saw. Here's one of the burrows that has been excavated. These were cemented up, preferentially meaning they became hard and rock. They were exhumed by storms. Then they roll around much like any piece of gravel, and they become rounded. And we can see these here. And these are the types of things that we might find the little organisms that like to live on hard surfaces on here. Okay, and you see there's quite a few here. This was one of the clues that this bed had cemented up at the bottom of the sea, on the ocean floor. This is what we call a hard ground. The burrows, this is rather a large one, but sometimes these are exposed, and if they were cemented, you might see the little organisms colonizing this. Okay, so it's going to look different than if the organisms were filling the inside of the burrow. Okay, or that these were things that were just stuck to the outside. And we may notice one on a block. If so, I'll point that out to you as we go by it. Okay, here we have a block of the Moseley that has tumbled down, and we can see on the surface, we can see how packed full of fossils it is. Unfortunately, these aren't ones that we're going to be able to dig out, but you can see little bivalves, clam animals, you can see some snails. Most things are broken. Here's some snails. We can see their coiled structure there. Okay. In the glauconite beds, it's easy to extract these, and they're in exquisite form. So let's go see if we can find some of these. Here we have the main glauconite, and in it we've got sort of this flat vertical area that's a little bit harder. We've got another one here. These are fractures that formed in the rock. Water has come down, and these are preferentially, they've got iron deposits on them, cementing this up. Iron often becomes a nice cement, and here we can see that it's exposed. Okay, so this was a little fracture that has been lined with this iron-rich material cement here. So as this outcrop here is eroding, since this is a little harder, it stands out in relief from the glauconite beds that it's cutting. The Houston Gem and Mineral Society on their website has not only the stratigraphic column, but they also have a key. So when you come fossil hunting here, you can key out your fossils. Here's some of the snails, very common. Here's some of the little bivalve clam-like organisms. We have little solitary corals. We have little otoliths. They look like little sort of lentils or beans. These are an ear, a bone inside the fish that allows it to hear. Sometimes they're just called fish ears. Shark's teeth, if we're lucky. And we find this little beak-like fossil. This is the internal shell of a little cephalopod, similar to a cuttlefish, called a belophonid. If we're lucky, maybe we'll find one of those. While there's a lot of things here, we just can't get to them because they're cemented. We're going to walk upriver past the railroad bridge and collect in softer units, sort of these green clay-like layers called the glauconite beds that are exposed on the other side. Let's go look at those. Here we are at the main glauconite, below the Moseley. The Moseley is that hard ledge up there that's vegetated at the top of the bluff here. This is a very soft material. It's clay. It's called the glauconite beds. We did some XRD over at Texas A&M on this. It's a closely related clay called chamosite, but everyone's so used to calling it the glauconite beds, we're going to go with that name. Now, one of the things we need if we're collecting here, a butter knife would work. I have these trowels that I picked up, And I'm going to give you all a trowel.
John, you get a trowel.
Okay. These are instrument of collection here. With these, if you find something you want to see, you want to dig around it. Don't stab it because you're going to break it. They're very soft. There's lots of little fossils similar to those we saw in the Mosley bid throughout this. And we're going to do a little bit of collecting here to see. I want to say one thing about this clay-like layer. What it is, it didn't wash in. It was produced by the organisms living in the waters above the ocean floor, as well as the little organisms living on or within the sediment there at the ocean floor. As the clams filter out their food, they also get particles on their gills that they clean off. They also excrete their waste. Little snails also. Snails are very notorious for fouling aquariums. They're big poopers. But what this is this is all essentially little fecal pellets that have piled up over time, and they've converted to clay. There may be, fish and stuff have also contributed to this. Because this is the chemistry on this clay, and within the sediment it became a low oxygen environment, the little calcium carbonate fossils of the snails and the bivalves, it's allowed them to be preserved. Oftentimes with snails, they're made of a mineral called aragonite, whereas the little clams are made of a mineral called calcite. They both have, the formulas are the same, CaCO3. It's just that the crystal structure of the aragonite is not stable and it converts. And the snails, poof, don't make good fossils. They usually dissolve away. But here, because of this clay chemistry, they're preserved. So we get many snail fossils out of here you normally would not see if you went to another outcrop of this age. Okay, so let's do some collecting and see what we can come up with.
Oh, okay. Okay.
See, and on the other side it's brown.
Right. Okay.
There's a shell, anomia. Sometimes that's called a baby foot shell. You can pick those up in Galveston. Here's one of the little unique things here, a bryozoan. I'll show that to you in a second. These are little organisms. Sometimes they're called moss animals. This one looks like a little coolie hat.
Huh.
And this one is a walking bryozoan. This is, here, let me put it in the sun. Okay, we've got a fish ear here. See, that looks like a little bean or lentil. Let me scooch it over there, and that side's a little bit wrinkly. Here, this, if we can look at it in profile, you see it's sort of conical. Looks like one of the little Chinese coolie hats.
Oh, that's why you called it that.
And when we flip it over, there's the underside. Now, this is a colonial animal. There's many hundreds of little organisms, the little bryozoan that lives here. This one's very unique. Most of the bryozoans, they're encrusting, they grow on things, they might be branching. Some are soft, some are hard. This one makes a little hard shell. This one's called a walking bryozoan because some of the members of the colony have a long sort of spine that comes off of it, and if they don't like where they're at, they can actually move. They will walk away. They're not fast travelers, but they can, move. So that's very unique to here.
What are these two guys?
You've got two snails. So this is one that we call a high-spired gastropod. We can look it up on the chart. This is one that's also, this one's broken. There'd be more of it out this way and this way. It'd be very sort of elongate. Like, yeah, a cone, a long cone. These are sometimes called olive shells as a common name. Looks like a little olive. Mm-hmm. And then when we look on here it is, pseudo oliva. See here? Mm-hmm. Right there. So there's that one, and that's a very good one. See, the nice thing here, this normally would have been dissolved away. The glauconite chemistry has preserved it, and it's kept it in fairly good shape there. A little bit of breakage right there at the aperture where the little snail would come out. Mm-hmm. But good find.
Thank you.
What we found here, we found a concretion, and this is a type where the sort of like a big nodule. The outside is hardening. Okay, if I can flip that over. Okay, looks like a rock, but what happened is this one has what we call differential cementation. You want to flick that over there so we can see the inside again.
Softer material here.
This was softer material on the inside. So here it looks like it's a very hard clay, but you can see it's eroding away. Sometimes you crack these open, they're full of sand. We've spent a little time digging through the main glauconite here. Can you hand me a trowel? So again, if you have a butter knife or a trowel, if you find something, you want to sort of dig around it. Don't stab at it because they're very crumbly and delicate. So many times you've just are picking things up off the surface here. I found a nice little snail here I'll add to our collection. So what we've got is we got some clam-like organisms, bivalves. Here's our little baby foot shell, which is here, anomia. You can pick these up on the beach in Galveston. This guy is still around. They're very delicate, but they've been preserved because of the glauconite, and these do get fairly large. I've seen them larger than this one. Here's some other bivalves. Here's a different variety there. Again, you can see the ribbing on them. They're just beautifully preserved. Here's our collections of snails. There's some more over here. Our olive shell. This is a cone shell, which is here. Today, this species is still around. They're very colorful shells. You can find them in different stores and such. Brown and white, very beautiful pattern. Of course, being 35 million years old, the coloration no longer exists. The unique thing about these is the living ones, their flesh is poisonous, and some of them are very poison that tourists will pick them up, and they have killed people. We have some little coiled shells, a lot of beautiful little ribbing, ornamentation on them. Here, let me pull that one out. This is a scaphopod. Here, you can find these along the Pacific Northwest, as well as other places. But sometimes it's called a tusk shell because it's very elongated. Here's our little bryozoan we found earlier. Here's our collection of otoliths, our fish ears, so to speak. With these, some of them, depending on the ornamentation, you can tell what kind of fish you have. I can't do that, but the size, the shape, whether it's wrinkled or smooth, it will give an indication of what you have living in the waters above. The unique thing about this is if you cut them, they have rings on them. For as they grew, they put on a layer of calcite each year. Right, yeah. So, the bigger ones is an older fish.
We have come to the end of our exploration of the geology of the coastal prairie. We learned something new at each of the 4 sites we visited. But most of all, we learned that there is much to be seen if you look closely. We leave you with a passage from Goodbye to a River by John Graves. Published in 1959, Graves wrote the book to commemorate his journey down the Brazos River in advance of the changes to the river that he believed would occur if a series of proposed dams were built. His words resonate with us still today. Canoes, too, are unobtrusive. They don't storm the natural world or ride over it, but drift in upon it as a part of its own silence. As you either care about what the land is or is not, so do you like or dislike quiet things, sailboats, or rainy green mornings in foreign places, or a grazing herd, or the ruins of old monasteries in the mountains. Chances for being quiet nowadays are limited.